Hi, I'm Niall Williams. I'm a PhD student at the University of Maryland, College Park, and I'll be talking about our recent TVCG paper called ARC, Alignment-Based Redirection Controller for Redirected Walking in Complex Environments. And this is joint work with my PhD advisors, Aniket Bera and Dinesh Minocha. So one of the main appeals of virtual reality is being able to interact with and do things in very varied and wide and complex and expansive virtual environments. And oftentimes, a core component of that interaction with the virtual world is being able to explore that virtual world. And so because of this, we need to develop different ways to allow users to naturally and easily explore these large, expansive virtual environments, since it's such a core component of the virtual experience. And when we talk about virtual exploration or VR locomotion, we're talking about a physical environment and a virtual environment, the user located in both of these environments, as well as the obstacles in either of these environments. And then when the user wants to walk on a path in the virtual world, they usually have to walk on that same path in the physical world. However, this leads to a fundamental problem in VR locomotion. If the user wants to walk on an unobstructed path in the virtual world, it might correspond to an obstructed path in the physical world. This happens because the layouts of the objects in the two environments are different. And so to get around this problem, many different locomotion techniques have been developed over the years, including things like teleportation, motion gestures like walking in place, regular joystick controls, and omnidirectional treadmills. These are all just a few of the many different techniques that have been developed. And one thing to consider with these is that they all have their disadvantages and their advantages when it comes to things like the user's sense of presence in the environment and the user's ability to easily explore the virtual world. In this work, we'll consider redirected walking, which is a locomotion technique that allows the user to explore the virtual world using natural walking. Natural walking is often preferred because it's very intuitive, so it's easy for the user to learn, and also because it affords a higher sense of presence in the virtual environment, which means that the user is more comfortable in the virtual world. The way redirected walking works is that the virtual environment is slowly rotated around the virtual camera while the user walks around. And if these rotations are slow enough, the user doesn't actually notice them happening in real time, but they subconsciously adjust their physical trajectory in order to counteract the rotations and remain on whatever path they intended to walk in the virtual world. And so the end result is that the user walks on a physical trajectory that differs from their virtual trajectory. And so we can use redirected walking to steer the user around in the physical world and have them avoid objects. And so the speed of the virtual environment rotations that we do in redirected walking are controlled by parameters called redirection gains, or just gains for short. And so when you have a strong redirection gain, the virtual environment rotates faster, which corresponds to a physical path that deviates more from the virtual path. And this is good because it allows us to more easily steer the user around in the physical world so that they can avoid objects. But it's bad because this means that the virtual rotations are more noticeable to the user, which means it's more likely that they'll actually consciously notice them, and then it'll detract from their experience and it could make them feel sick. And then on the other hand, we have weak redirection gains, which means that the virtual environment rotates more slowly, which corresponds to a physical path that deviates less from the virtual path. And this is good because it's more comfortable for the user because it's harder for them to actually notice the virtual environment rotations. But it's bad because it means we have less ability to steer the user around in the physical world. So it becomes harder to avoid objects in the physical world. And so there exists this sort of trade-off between the redirection gain strength and the user experience. A redirection controller is an algorithm that seeks to manage this trade-off. A redirection controller applies redirected walking gains on every frame during the experience to steer the user around in the physical world. If the user gets too close to a physical object, we initiate what's called a reset maneuver, or just a reset for short. And what this is that the user is paused and they're prompted to stop walking, and then they are instructed to turn around. And once they've turned away from whatever object they got too close to, then they're free to walk again. And so the redirection controller's main goal is to steer the user around in the physical world with redirected walking such that it minimizes the number of resets that are incurred. And this problem is interesting because for any given virtual path, there's multiple different physical paths that the user can be steered along. So it's not just these two physical paths in this diagram that I'm showing, but actually there's a whole range in between because the rotation gains or the redirection gains are a continuous value. So any different value of the redirection gains yields a different physical path. So there's a huge state space of different solutions to this problem, essentially, which makes it a very difficult problem to solve, especially over time as the path gets longer and longer. And furthermore, we also need to consider the human in the loop in this whole problem, because at the end of the day, it's virtual reality. So we really care about the user experience. So the reason this whole redirection problem is interesting is because it's an interesting intersection between HCI as well as algorithms in a huge search space. So over the years, many different redirection controllers have been developed, including things like steer to center, artificial potential fields, and controllers based on reinforcement learning. And these are just a few of the many different controllers that have been developed, just to show you a few examples. And an important thing with all of these different redirection controller algorithms is the amount of information that they require in order to work. And when we say information, we just mean anything related to the layouts of the physical and virtual worlds and the user's position in both of those worlds in the past, present, and the future. And so given this notion of information required, we can imagine this information required spectrum, and all the different controllers could be placed along it. And at one end, we have the least information required. So these controllers, which are typically known as reactive controllers, they don't need much information in order to work. And they only work based off, they only use information available on the current frame or on previous frames. And so as the name sort of suggests, they just react to the user's current position in the physical world and they steer them accordingly. So an example of this would be steer to center, which constantly steers the user towards the center of the physical track space, regardless of the user's position. Then we have predictive controllers, which, as the name suggests, predict the user's trajectory through the virtual world, and then they use that prediction to inform the steering that they do in the physical world. And so these controllers usually need to know something about the layouts of the virtual world in order to make accurate predictions about the user's trajectory through the world. And then at the other end of the spectrum, we have scripted controllers, which usually require the most information. These controllers steer the user in the physical world according to some predefined path in the virtual world. So they only work if the user follows that specific virtual path in the virtual world. And these controllers are able to perform better usually than the other controllers because they already know a lot about the situation and what the user's path will be. So they're usually able to incur fewer resets than other algorithms, but the downside is that they are not applicable to as many different situations because they require so much out of the user and out of the system. While on the other hand, reactive controllers are usually very generally applicable because they don't need to know much about the system setup, but they tend to perform worse. So this highlights another trade-off that we have to deal with, which is a trade-off between the amount of information our algorithm needs and how well it performs. So ideally, we would have an algorithm that achieves high performance, which means a low number of resets, but also doesn't need a lot of information in order to work. And it's proven to be pretty hard to come up with one of these over the years. And so for this work, we'll consider only reactive controllers. So these controllers only operate with information available on the current frame and any previous frames. And then there's one user in the physical and virtual world. And one of the common assumptions of the work that we compare against in our work is that the virtual environment is infinite and empty. And so this is usually done because the reasoning is that, well, the algorithms are designed to work in any type of environment. So we don't really care what that virtual environment actually looks like. Furthermore, there's an infinite number of virtual environments that are out there. So it's not possible to test in every single different environment anyway. So with that reasoning, the prior algorithms essentially just ignore the virtual environment. And where our work starts is with a question of whether that's actually the correct thing to do, or if that's perhaps hindering performance. Because if you recall, the whole reason why the VR locomotion problem is a thing in the first place is because there's a difference between the physical and virtual environments. And so by ignoring the virtual environment, you're essentially throwing out almost half of the information of the whole problem. And so we thought, is there a way to bring back the virtual environment information into a reactive controller and have that benefit our performance? And as it turns out, this seems to be the case. And I'll illustrate how with these two examples. So consider this pair of environments. If the user wants to walk forward in VR, they can't do it because they'll walk into the object in front of them in the physical world. This is the same problem that I've mentioned over and over now. But if we consider this new pair of environments, notice that the layouts of the objects in the physical and virtual worlds is different. But if the user wants to walk forward in VR, they're able to do so in the physical world without any collisions or without getting too close to any objects. And so this highlights the key observation that we made with our work, which is that you can have a physical and virtual world that are globally dissimilar, but they can be they can be similar on a local scale, and that this local similarity means that the user is able to walk on collision-free paths. And so just to reiterate, because it's important, and it's the key observation we made, you can have different environments, and that these environments have regions of local similarity, and that these regions of local similarity lead to collision-free paths when the user is located in both of them. And so this whole idea of measuring the differences and comparing the similarity between the physical and virtual environments, we call this idea alignment. And we've seen not much prior work that formally studies this idea, except for a few recent works by Gerald Thomas et al. And despite the low amount of formal work studying it, we think that this is actually pretty intuitive for VR researchers, and that it's probably something a lot of people are already doing, at least informally, maybe without even realizing it, but that we haven't seen many people studying it formally. And so with this idea of alignment that we can use to measure the similarity between environments, we developed our alignment-based redirection controller, or ARC for short. And so the way it works is that first we have to measure the similarity between the two environments. And we do this by measuring the distance to the closest object in front of the user, as well as to the left and right of the user. And then once we have these 6 values, which we can compute with simple ray shooting queries, which we've all come to know and love in the graphics community, we can then measure the alignment score of this person's state in the environments as the sum of the pairwise differences of these different distances. And so now that we have this notion of alignment and a measure of the similarity between the two environments, we can use our algorithm to have some heuristics to set the redirection gains for the user. So we set 3 different redirection gains, which are applied according to the type of movement that the user is doing, such as walking in a straight line or turning in place. And for each of these different redirection gains, we set them according to either the difference between the physical and virtual distances to objects, or according to the differences between the previous and the current alignment, between the previous frame and the current frame. And then while we set these redirection gains, we also make sure to limit them to be perceptually acceptable. So what this means essentially is that we make sure that the redirection gains that we apply are not too fast so that the user notices them and that it would detract from their experience. So this is how we account for the user experience portion in our algorithm. And I'll show some examples now of how our algorithm works. So in this pair of environments, the user wants to walk forward. And if they do this, our algorithm steers them towards the center of the physical space on a lateral level. And by the end of the time that they finished walking, their proximity to objects in the physical and virtual worlds is the same. And here's a user demo of this. The user walks forward in VR, and in the physical world, they get steered away from the tracking space boundary and towards the center of the tracking space. And then in this second example coming up, the user again walks forward in VR, and then in the physical world, they get steered away from the object in front of them and away from the tracking space boundary to the left of them, towards the center of the physical space. And then as they approach the other edge of the tracking boundary, they again start to get steered away. And so to evaluate our algorithm, we tested in 3 different pairs of physical and virtual environments. And we also compared our results against 2 state-of-the-art controllers, reactive controllers, which are steer to center and artificial potential fields. And in order to get a lot of data to make some statistical claims about the performance values, we ran simulations of users walking through the virtual world on collision-free paths, and then we steered the user around in the physical world for their corresponding paths with all the 3 different algorithms, which is our algorithm and the 2 that we compare against. Here we show a visualization of the algorithms in action. So in this, we're showing the virtual environment in orange and the physical environment in green. So while the user walks around, the virtual environment gets rotated around, which you see is the rotating orange square. And then if you see with our algorithm on the left, eventually the user's state in the physical and virtual worlds will match up exactly. And then the 2 environments will be overlaid on top of each other. And at this point, the user doesn't incur any more collisions or resets with physical objects. but the other two algorithms, they can't guarantee this notion of matching the physical and virtual worlds. And so they continue to have resets where they get too close to physical objects. And here we show a heat map of the user's position in the physical world in one of the environments. And this is across 100 different paths that the user walked. And yellow in these diagrams means more time spent there, and purple means less time spent there. And so what we can see is that with our algorithm, the user is able to explore a larger percentage of the physical world than they were with the other algorithms, which tend to get the user stuck in pockets of space. And when we looked at the number of resets that were incurred across all the multiple paths in each of the different environments, we found that our algorithm achieved significantly fewer resets than any of the other algorithms in all three of the conditions we tested. And then what I think is probably the most interesting result out of all of this is that we also looked at the steering rate of the different algorithms. So how fast is the virtual environment rotating around while the user walks in the physical world? And if you recall from earlier in the talk, I mentioned there's a trade-off between the speed of the rotations and the performance. So usually, in order to get better performance, aka a lower number of resets, we usually need to rotate the virtual environment at a faster rate. And this is bad because it's more noticeable to the user, so it's more likely that they'll start to feel sick and it detracts from the user experience. But we found with our work actually that with our algorithm, we're able to achieve significantly better performance. So we achieve significantly fewer resets, but we're also able to do this while steering the user with less intense gains. So the environment with our algorithm rotates slower, but we still achieve better results than the other algorithms. And I think this is the most important or interesting result because it sort of goes against what we used to think was the case. And it shows that by leveraging this whole idea of alignment and measuring the differences between the physical and virtual worlds and incorporating that into our algorithms, we can achieve significant benefits for both the algorithm performance as well as the user experience, which I think is a really interesting idea. And I think this shows a lot of promise for this whole idea of alignment. And so in summary, we showed that the physical and virtual worlds can be globally dissimilar, but that they can have areas that are locally similar, and that steering the user in these areas of local similarity yields significant benefits, including things like achieving significantly fewer resets and allowing the user to explore a larger percentage of the physical world, and steering the user with less intense redirection gains, which yields a more comfortable experience for the user. And so with this work, we hope that other researchers in VR locomotion and maybe even outside of VR locomotion, just in VR, can make use of this idea of alignment and start to come up with other types of metrics to measure similarity and measure alignment between the physical and virtual worlds, and that we can start to more formalize this idea and use it in more algorithms, since it's shown now that it can be beneficial both for algorithm performance as well as for user experience. And with that, I'd like to briefly thank my advisors, Aniket Bera and Dinesh Minocha, for their continued support and guidance throughout all this work. And if you have any questions, you can contact me with that email at the bottom right corner. And the paper is available and the code is also available online at those two links. Thanks very much for your attention.